What's up guys, Shawnthebro here, and we're back for another episode of the fighting game tutorial series. In today's episode we're going to be going over Rollback Netcode Part 1. We're finally here. So Rollback Netcode is a very important part of many fighters. For those that don't know, it's essentially a type of netcode or type of multiplayer where the game is deterministic, which means no matter how many times you run through a simulation, you'll always get the same result. Unreal is non-deterministic by default, and mainly for things like physics, because there are other forces in play here like friction and acceleration. If I tried to roll back a given number of frames, I couldn't actually do that simply in Unreal. So to accomplish rollback netcode in our Unreal game, we need to override some things, we need to make some custom logic, and we need to support that rollback architecture to do so. The end result is typically a much smoother game with very low latency and very good response time, even in online play, regardless of the user's connection strengths and speeds. This is one of the things that we've set out to tackle in this series, and we have a few episodes that touch on some of the topics we need to do to support rollback. So today's episode is going to be going over more of those things that we're going to need to do, and this is going to be one of the most important episodes because, as I mentioned, rollback netcode needs to be deterministic. And what we're going to do in today's episode is make a fixed tick or deterministic tick, which will allow us to do things like store states and keep inputs so that no matter how many times we try and roll back the frames, we're always going to get the same result. This is the key to rollback netcode. Now, before we hop into this episode, if you want to check out the entire series so you can see how we're doing things in here, such as hitboxes, hurtboxes, regular multiplayer, local multiplayer, practice mode, and a whole lot more, I'll link you to the entire fighting game tutorial series right here in this playlist in the top right corner. Alternatively, if you don't care about that, you just care about rollback netcode, that's perfectly fine. You don't have to watch the whole series to follow along. But I do recommend that you watch the other rollback episodes. So we have one episode specifically before this one called Rollback Preparation Part 1. And that's going to go over some things that are very useful for rollback netcode. And we're going to be expanding upon that sort of ideology and those concepts today. So I'll link this right here in the top right corner as well. Now with that said, we can go ahead and get started. So this is a code and blueprint tutorial series. We're going to be doing everything in C++ today. And in general, when we're dealing with netcode and rollback, it's going to be almost entirely in code just by the nature of it. The first thing we need to do is make some sort of class to manage how we're getting updates, storing information, triggering a rollback, and other things like that. So I'm going to make a new class. I'm going to make a C++ class, so I can go to C++ classes. Go in this folder. Now, note that this episode will work in UE4 or UE5. It's going to be pretty much the same process for both. Once we're in our C++ classes, we can right-click and go New C++ Class to add one. When we're in here, I want to go to All Classes, and I want to search for Game Instance Subsystem. Now, subsystems aren't really something we've gone over in the series, but Unreal has this amazing thing called subsystems, which essentially makes a class that goes alongside with one of Unreal's built-in classes. As you see in this comment right here, it says, subsystems are auto-instance classes that share the lifetime of certain engine constructs. So for example, a world subsystem is a subsystem that gets created when a world is loaded, and it persists for the existence of that world. So if I load into a map, that subsystem is valid and will be valid until I go to a new map. In this case, the Game Instance Subsystem is made alongside the game instance and will exist for the entire time the game instance is valid. This is good for traveling, which is very important in online multiplayer because we need to make sure all of our data is correct when we're traveling in a multiplayer scenario. But really, we want our whole game to support rollback so that we can do whatever we need to do with it. So Game Instance Subsystem is going to be the parent class, and I'm going to call this Rollback Simulation Subsystem. You can call this whatever you want. You could call it Rollback Manager, you could call it Simulation Subsystem. The reason I named it this is because I want to be very explicit about what we're actually doing here. Rollback is a form of simulation. You are rolling back frames after making a prediction so that you can match what actually happened when you receive the data packets. So this is simulation, and I want to be explicit again about the fact that it's rollback netcode specifically, because you could have a simulation subsystem that's not rollback. Even more generic, it doesn't have to be a simulation subsystem. You can just simulate something and it doesn't have to be rollback supported. So I'm just saying rollback simulation subsystem. Feel free to name it whatever you want. This is just what made sense to me. Like I usually do, I've already made this class. That way you don't have to see me hot reload or close the project and reopen the project to get this class in here. But once you have this ready, you can go ahead and select create class, and then it's going to either make it here and hot reload if you're in UE4. If you're in UE5 like I am, it's going to live code. Or if you did these things without having launched through an IDE like Visual Studio, it will likely ask you to just reload the project, so you'll have to close out of it and relaunch. One way or another, once it is finished, you should see your class in here wherever you made it. So I made mine Rollback Simulation Subsystem, and I have a .cpp and a .h file. What you see in here is pretty much exactly what you should have. And if you're not able to use a Game Instance Subsystem because you're in a version of Unreal that doesn't have this is relatively new, you could just do this in the game instance. Game Instance Subsystem just kind of helps you keep it separate from the game instance, so you don't have to put everything in that class. You could handle this in other classes too. You have a lot of options. This is just where I chose to do it. Now this class is very empty to get started with. There's two things in particular that I want to add for today's episode. The first is the way that we actually determine how many times we have to update. So when I say that there's a fixed tick, that means it's going to be ticking at the same rate. If you look at a tick of a different class, like the character, the fighter template character, if we scroll down to the tick function here, you'll see that Unreal ticks have a float delta time passed into them. And this means a frame can occur, and then delta time passes, then the next frame plays. Really, the way it works is we're done working on a frame, so we load the next frame. But delta time is how much time passed between those two frames. The whole reason this exists is so you know the difference in the frames, because frames aren't really a set period of time. They can take longer to finish than average or shorter to finish than average. It's not a set period of time. With a deterministic view of things, we need to make sure it is a set amount of time that has passed. If it's not, we cannot roll back, because if we roll back based on the time that was passed in, what other things changed in that amount of time? Could be the character's acceleration, could be, again, their friction. We're not going to know all of that data if it's not deterministic. So instead of doing this, what we're going to do is have the engine run the tick on the Game Instance Subsystem that we made, the Rollback Simulation Subsystem. We're going to set an amount of time that we want to allow to process this data. That's our fixed tick rate. Determine, based on the delta time, based on how much time has passed, how many fixed ticks we need to perform. So a standard value is 1 divided by 60 or 1 divided by 120. A lot of these games run at 60 or 120 frames per second. So 1 divided by that number gets you the time in seconds that we want to process on our fixed tick. This probably sounds pretty confusing, and it kind of is until you get the hang of it. So let's go ahead and get into it, and it should make more sense. Let's go to Rollback Simulation Subsystem.h. We're going to want two things, like I mentioned earlier. The first is our fixed tick, and the second is the way we're calling that fixed tick. So let's go ahead and override initialize for Game Instance Subsystem. So void initialize f collection, or I think it's f subsystem collection base. Yep, that's it right there. Reference collection. So this is just an override for initialize on a Game Instance Subsystem. You can think of this as a begin play for the Game Instance Subsystem. It's not the same, it's not an actor, it doesn't have begin play, but this is when it's ready to go and ready to be used. So say the Game Instance Subsystem is ready to be used, or is initialized is fine, honestly. That makes enough sense. Then we're going to need to make another function for the fixed update. The fixed deterministic update. And we'll call this void fixed update, or fixed tick. Let's call it fixed tick so that it fits in more with how Unreal does it. And we'll change the comment to say update slash tick. So the fixed deterministic update slash tick. Void fixed tick. And we can start filling these out. There's going to be a little bit more that we need, and you'll understand why in a second. If we go to rollback simulation subsystem.cpp and add our functions here, so we want to have void u rollback simulation subsystem colon initialize, and it was f subsystem collection base reference collection. This is our first function, and then the other function we made was our fixed tick. Void u rollback simulation subsystem colon fixed tick. For initialize, we want to make sure we call the Game Instance Subsystems initialize function. So this is easy enough. We're just going to call super : initialize and passing collection. Literally just call the parent function or initialize. Then we're going to do our own logic underneath of it as well. In here, we want to call our fixed tick, but of course this isn't enough information. If we call it in here, we'll just call it one time when initialize gets called. We need this to keep running forever, or really we need it to keep running for as long as this class is still running. And to do that, we need to know how much data we have to process. This is what I was mentioning earlier. Frames are not a set amount of time. So if we were to do division on, say, 1 divided by 60, this would get the time that passes for one frame at 60 FPS in seconds. And the result, I believe, is 0.016. I believe it's like 6, 7 repeating, something like that. So if our fixed tick is aiming for 60 FPS, then we say this is the amount of time that we can pass before we have to process that information in fixed tick. So when we're updating and we see the delta time change between updates within Unreal Engine, we can determine if we should call fixed tick. If more time has passed than this, or really if this amount of time has passed or more time has passed, then we should call fixed tick. If, say, double this amount of time passed since the last tick, then we need to run fixed tick twice. If not this much time passed since last update, then we don't need to run fixed tick yet. Not enough data has passed to look at the state of the game, look at the inputs pressed, all those things. Instead of just calling it one time, what we can really do is call it whenever the world ticks, or whenever the game ticks, because that's how we're going to know how much time has passed based on that delta time that gets passed in the tick. And there are a few different ways you could do this. There is something that exists called fWorld delegates, and you can do : on world tick start, which means every time tick starts for the world, we can bind something to this. So we can perform logic on our side, and that's really where we would call fixed tick, because then we would have our update delta time, and we would know that we're ready to process new information if we're above a certain amount of time passed. So this is the perfect spot for it. After on world tick started, you can do .add lambda. A lambda, if you're not familiar in C++, is basically a function that you're doing in place instead of making a new function for. So it looks pretty confusing when you first look at it, but literally just think of a lambda as a function that you're doing in place. Usually you would use them for things like piece of logic that you want to separate from the rest of the code, but you don't intend to call it from anywhere else or do it another point. And I think a lambda also makes a lot of sense here because we're never going to be calling fixed tick directly. It should be coming from the game telling us that an update has occurred. So this makes perfect sense to me. Remember I said lambdas are kind of weird if you haven't seen them before? Lambdas follow this structure where they have the capture list, which is in these brackets right here, and then it has the arguments as well in parentheses, just like a regular function does, just like this. But the capture list here, the brackets, means we can grab variables that are outside the scope of this lambda, like if we want to have local variables from the function invoking this lambda within the lambda body. So for example, if I had a variable here like int I equals 0, when we do this lambda logic, the function doesn't have access to int I unless I put it in the capture list. Think of if fixed tick had a parameter here for int temp. Okay, it doesn't matter what this does, just it had a parameter we had to call. Well, if I make int I here before I call fixed tick, I can't just get I in fixed tick, right? I doesn't exist. It was made in this other scope. Well, a lambda, again, is really just a function. So I doesn't exist in here either. But if you capture it, if you were to add it in that capture list, literally brackets I like this, you will have access to that variable. So let me clean this up, remove my example here. And we can also remove this fixed tick that I placed originally because we're going to do it in the lambda. So it should look like this now. Now go in your parentheses, add the brackets, and you can put this in here. This just means you're capturing everything about this class. So any variables you make in Rollback Simulation Subsystem will be available in that function. So now we have this, and just like other functions, remember, you have to put parentheses for what's being passed in to that function. So onWorldTickStart specifically is going to pass it parameters. We're not making the parameters. Binding to onWorldTickStart does require us to accept some parameters. And the parameters are going to be the world. So uWorld pointer world, e level tick, tick type. And the last one is going to be the really important one right now. That is our delta time. So float delta time. After you've written this lambda, it's pretty customary to enter. Notice that I have one other parenthesis here. So I have the parentheses closed for the parameters, but not for the add lambda. Then we put curly braces, just like you would a function. And I like to personally put my curly braces in line with the lambda here. A lot of IDEs try to space it out. I just like to treat it like a regular function. So I like to put my stuff right here. But however you want to organize it is fine. Take note that we have curly braces, and then we have a parenthesis, and you put your semicolon at the end of the parenthesis, because this is all technically part of this line here. We're just breaking it up so it's easier to read. I mean, technically you could put everything on the same line, just like this, and put your function body right here, like int I equals 0. But that's a lot harder to read than just setting it up like a function. So I like to do it like that. But now, whenever the world ticks, we're going to get these three parameters. And again, delta time is really what we want. In here is where we're going to call fixed tick. We're still not ready to call it yet because we need to check and see if enough time has passed. But we're getting closer. Now what we need to do is tally up or add up how much time has passed. Remember, I was saying it could be not enough time to perform a fixed tick, or enough time to perform one fixed tick, or if it's double the amount of time we expect for a fixed tick, we could actually have to call it more than once. And we can do that with something typically called an accumulator. It's just accumulating the delta time, or the time that's passing. I think that term can be a little confusing, so we can call it something like float time accumulator. That way we at least know what we're accumulating. The amount of time, let's say the time in seconds of data that needs to be processed. And I think this makes sense. If it doesn't, it probably will after we implement it here. Also, I'm going to put this in public, and I'll put these ones in private, just to keep our class nice and clean here. Now we have our time that we want to add to whenever time passes, and we can do this simply by typing time accumulator plus equals delta time. So as time passes, we're adding it to the accumulator so that we know how much time has to be processed. Then we can just check to see if time accumulator is greater than or equal to, and this will be our number that we want to use for our simulation step, or our fixed update. So this is that number I was showing you earlier, like 0.016677, something like that. We should make this into a variable, and we should determine what we want this to be. So this could be 1 divided by 60, it could be 1 divided by 120. Really, it can be any number you want. It's how frequently you want to perform your fixed tick. Let's start with 60 FPS for now because it's pretty simple to do that. Okay, let's make a variable for it. So we'll say the time in seconds to represent the rate of the fixed tick. I'll say fixed update / tick just to be consistent. We'll call this float fixed step time. And let's actually change this comment as well. The time in seconds to represent the step, say to represent how often the fixed update / tick runs. I think that makes a little bit more sense, but I think you get the point as well. So essentially, this is how much time is required for us to perform a fixed tick, or a fixed update, or a step. And this is how much time has actually passed in the world. So now if we go back to the CPP, we can check if time accumulator is greater than or equal to fixed step time. And if it is, we'll finally call fixed update. Fixed tick is actually the name of the function. And let's change this from an if to a while, actually, because like I was mentioning earlier, we could have to perform multiple fixed steps depending on how long it took for the world to actually tick. Say it took 8 times as long as our fixed step time, we need to perform 8 fixed steps, or 8 fixed ticks. Perform a fixed update if enough time has passed in the world. So there we go. I think that makes a lot of sense now, and we should be calling fixed tick at that given interval, but we need to set up what the fixed step time is, and we should initialize the time accumulator as well. The Game Instance Subsystem does have a constructor, but it does get called a few times. In my experience, it seems to be better to call things or set up logic from initialize instead of the constructor. You probably could set these variables in the constructor, but for now I'm just going to put them in here, and we can always move them later if we choose to. So fixed step time is going to be equal to whatever number we choose. We could either manually put it in here, like do the math, set up our value, say, yep, this is the rate, or we can do fixed step time equals 1 divided by the number that we want. So if we want to do 60 frames, that would be just 1 divided by 60. For this simple example, we can just do 1 divided by 60. So say set initial values for variables, default values for variables, and then we will set time accumulator to 0.0f. And 1 divided by 60 is definitely not what I should be doing here. I should be doing 1.0f divided by 60.0f. So it doesn't go from integer to float, but float to float. So we have our 2 floats here. Now we have our value set up. Fixed tick will be running whenever enough time has passed. And in fixed tick, we can do our logic, like processing inputs, checking states, things like that. In today's episode, we're just going to print a log and make sure it's printing out when we would expect. If we do that and our fixed tick is working, then we're good. We don't have to worry about anything else. So another thing to note, because this might look confusing, you're like, in initialize, this is only going to get called 1 time. When we add the binding here, this set of logic is going to run every time it updates. The tick from the world is technically calling this function. That's how you can think of it anyway. It's a little bit more complicated than that, but basically the tick from the world is just saying do this logic. And now let's add a simple log in here. So we can just do UE log temp info text, and for our text we can say fixed tick performed. Fixed tick performed successfully. And I'm sorry, it's not info, it is log. I was thinking of a custom logging system that I use. That is completely wrong. It should just be log temp log, then your text. Perfect. And then if we actually try to run this, it should work. We should print this, but the last thing that we have to take care of is what actually happens once we process this data. Because right now we put this in a while loop, which is just going to keep running, checking this condition. And since it's ticking, it's going to be adding more time to it, which means it's going to eventually always be greater than the fixed step time, which means we're eventually just going to always be printing this. This while loop will never complete. So we need to decrement. So we need to decrease the time accumulator by how much time we used, how much time we caught up by. And that's going to be our fixed step time. So after we update in our fixed tick, we just do time accumulator minus equals fixed step time. Because this while loop will keep it here. We won't keep adding to it while we're looping through. So if we have to update 8 times through the fixed update based on the amount of delta time that came in, it will run all 8 times, and then it will no longer be greater than or equal to fixed step time, so it can end the while loop and then proceed forward. So with this done, if we go ahead and launch the editor is back open. We can now launch. You'll see we don't get stuck forever, like I was saying, which we would if we didn't do that subtraction, and you can see that the log is printing. This shouldn't impact anything else that you're doing. The game should still function as expected. And if it does, and you can see that it does, then we don't have anything to worry about. We are good. If you enjoyed and you're looking forward to more Rollback Netcode episodes, please subscribe and consider checking out the Patreon, YouTube membership, or Discord subscriptions to benefit myself and the channel, which helps me make these videos and learn more content for you guys. And it also gets you some benefits for doing so. Thank you so much to everyone who has. If you ran into any problems following this tutorial or any of my tutorials, feel free to join the Discord community. There's a link in the description, and I would be happy to help you out. That support is completely free. Thank you guys so much for watching. I'm Shawnthebro, and I'll see you in the next one. Goodbye, guys.